I'm Semiha Yılmazer. I'm from Bilkent University in Turkey. Our first presenters, could you introduce yourself, tell your name?
Hi everyone, good morning. My name is Arshdeep Singh. I'm a research fellow and sustainability fellow in University of Surrey, and also early career cost champion for AI and data within UK Costing Network.
Yeah. Happy to see that.
Thank
Stage
you.
is yours.
Okay, thank you very much. So that's good. So thanks for coming today. So today I'm going to present my work on sound recognition, recognizing various sound activities in the surrounding using EPANs, which is an efficient version of pre-trained audio neural networks. So today I'm going to follow this outline. First we'll give a background on sound and its importance, different application areas, then a system using AI and ML, artificial intelligence and machine learning for sound recognition. Then we'll talk about shortcomings of such frameworks. Then we'll discuss proposed strategy for obtaining efficient AI ML framework. And in the end, I will finish with the performance analysis and final remarks. So if we see in our surrounding, there exists abundance of information. For example, various sound activities such as smoke alarm, speech signal, like I'm speaking here within this venue, baby cry event, water tap, ambulance. So such sound events, such sound activities, they yield abundance of information. And with AI, with artificial intelligence, we can cover many applications from security, for example, within home, the glass break sound, if there's in offices or homes is there, so one can monitor surveillance kind of applications. Then in assistive living with the human support with using AI, so one can do that kind of application. And one can also monitor bioacoustics, biodiversity things within environmental by analyzing bird sound activities, right? And then multimedia, one can search video from a gigantic video sources using sound input. So there is a lot of potential with sound using AI. And typically the system that is used to build or recognize different activities is called an audio tagging system, where audio is coming from sound signal and tagging means to describe in plain language or plain English language, to tag something given an audio recording. Here in this figure I have shown this general audio tagging system where from the external world microphones are used to record sound signal. Then there is a AI ML framework which can tell you the top few categories which it predicts from this sound signal with their confidence. So let's see a demonstration how such system work. And here I will show a video where AI ML framework which is built within CVSSP lab in University of Surrey. So it uses sound signal and it tell you the top few predicted categories.
Okay, no more.
So this audio tagging system covers mostly all the events that occurs in the surrounding. And okay, so again, so based on this system, we build an hardware which is a very tiny device using Raspberry Pi thing. So let's see its demonstration as well. So how it works. So here the box shown here is a standalone device. You need to press this button of this device, and then it start recording or sensing things in the surrounding. And based on that sense signal and this predictor sound category, it will send notification to emails. So one can get notified as well using this sound signal. Let's see this. So this kind of system can be used in various applications, and one can get notification as well, and also record the historical set of events which occurred in the past. So for traffic noise monitoring, it can be used to analyze various sound activities. So the backbone of such system typically consists of a neural network, which is convolution neural networks, and it has shown promising performance for recognizing more than 500 audio events, which are on Google audio data set. And this system consists of a set of layers, which are convolution layers and pooling layers, and the system accepts raw audio signal as input, and then it transforms into Mel spectrogram, which are the time frequency representation corresponding to the audio signal. Then it maps this raw audio signal to one of the categories. And when this system is learned, so we use many examples to train this system to optimize the predicted classes versus the true output classes. And the system learns a set of filters, which are the parameters within this network, which do convolution operation. And a filter in a network is very important because it's learned through an optimization process, and it carries all the information which is learned from the examples. So this filter, one of the filter, it operates on whole input, and it produces one feature map, which is the output from the feature map, and one of the unit within the filter is produced by this operation, which is nothing but a multiply and accumulate operations. Let's see how this operation is performed. So given the filter, which has parameters, so filter operate on a patch of input, here blue patch, then it do this multiply and accumulate operation, and it produces the output in the next layer. So this way, the CNNs, they are very powerful in learning and in providing discriminative information, and they store information in filters and perform promising performance. However, there are shortcomings of such well-performing networks, which are the high computation complexity, so which arises from this multiply and accumulate operations, and this causes low inference speed, which means given an input, you will have the network will take more time to produce output. And then to solve nonlinear complex problems like more than 500 audio events, which covers mostly whole space, so they require a large number of parameters, so which causes high memory requirement when we want to deploy software solutions on hardware. This makes CNNs as resource hungry because they need resources, and hence they consume more energy when they run in real time. Although on softwares they perform really well, but when we want to deploy on real hardware, then there's big bottleneck because of these two things. And not only the resource hungry nature is a bottleneck, but also because of high energy consumption when we use many devices together, many networks together in IoT scenario. So then because of high consumption, they are not environmental friendly as well. So CNNs, they are in general machine learning systems with large complexity, they emit more CO2. For instance, when we train such high performing CNNs or machine learning frameworks for 48 hours, they emit CO2, which is equivalent to driving a car for 13 miles on an average. So these things are real bottleneck, particularly for edge devices, for example, smart watches or tiny devices that I just mentioned, I just shown that demonstration. So the problem with those devices that the devices will generate heat and they will slow down the whole system. It might burn out the system as well. So this is where we contribute in this work. So within this audio tagging system, which we designed for recognizing various sound events, so we come up with an efficient version of this AI/ML framework, where we reduce the parameter count from the baseline network from 81 million parameters to 23 million parameters, and we reduce this multiply accumulate operations approximately 30%, and also improve the performance as well. Here performance is measured in terms of mean average precision across each classes. Higher is better, just take with that. So we come up with this EPANS, which is a neural network, which is efficient version of PANS, existing PANS. And how we obtain this EPANS is, so we use pruning techniques where within the convolution neural networks, we remove few of the filters which are not important to contribute to the performance or in contribution to produce output for the next layer. So given a set of filters from a given convolution layer, we measure the importance of each filter in terms of how significantly they are in producing the output. And the significance of each filter is measured using operator norm of the filter, where we treat a filter as an operator which transform the input space X to output Y. And the significance of filter is measured using the operator norm of the filter, which is the sigma 1 value, when we decompose this filter into this SVD transformation. And sigma 1 higher means that the output is produced significantly corresponding to that filter, and which means that the information can propagate throughout the subsequent layers. So this way we measure the importance of each filter, and then we rank its importance, and based on the user defined pruning ratio, we select top few important filters from the network. So the whole process is we take a pre-trained network, then we do pruning layer wise layer. Then once we identify a set of important filters across each layer, then we obtain a prune network by physically removing the filters. And this network has lesser number of parameters and computations. Then to regain the performance, if there is a loss of performance because of eliminating few of the connections, we do a lightweight fine tuning, which is 20-30% of the original training efforts which are required to train the original model. So let's see the performance, how things work. So here the figure shows the performance versus the number of parameters. So we started with this baseline, which is this network, and it uses 100% parameter, and this red dotted line shows the baseline performance parameters. And then when we perform fine tuning, so the problem because of overfitting for the underlying task is not there, is getting reduced. And then removing more filters from the network with the same criteria, again we are still better than the baseline performance, and we have reduced more parameters as well. Approximately now we need only 30% parameters, which could give similar performance or better performance than that. And then when we remove 75% of the filters, so we find that when the parameters are 25%, then there is a trade-off between performance, baseline performance, and the parameters. So one can go with removing 25 of the parameters for this particular network to achieve similar performance, right? So what we gain with this after this pruning procedure is that, so when we compare these two networks, PANS, which is baseline one here with 100% parameters, and EPANS, so we can reduce this inference time, which is measured for 10,000 examples. So we could reduce time by 30%, which means your system is running 30% less time, and it consumes less energy for those time, because we are not using this 30% energy all the time, right? And then also we have reduced the number of multiply accumulate operations as well with the parameter reduction, which saves the memory, and which means that one can install such systems on mobile devices, which has a limit of memory, which is 100 MB. So with that, one can deploy such system on mobile devices as well. And also we improve the performance as well, the whole procedure, by opting the whole procedure. So the concluding remarks are, we come up with a strategy to reduce the computations of a pre-trained CNN. And given a pre-trained network, we can reduce its computations, and hence we can utilize the pre-trained network efficiently for the underlying problem. Let's say you're working on maybe less than 100 class problem, then it's a good strategy to first prune the network, then use for your purpose rather than using the whole network from the scratch. Thank you very much. So if anybody is interested in live sound recognition demonstration, so that's with me. We can talk and I can show you how the system work in real time. Thank you very much.
Thank you so much
Yeah.
for this outstanding presentation.
Thank you.